Okay, good evening everyone, and welcome to the first pilot lecture of 2016. It's meteorology this evening. It's a fairly long and extensive topic really, and it's quite difficult to teach directly to the exam or directly to what you want to get as pilots. So you've really got to go for quite a in-depth, broad coverage really to cover what you want as new pilots, what you want to pass your pilot exam, what you want to allow you to progress as you go forward. So it'll take a little while this evening. Hopefully we can get it done in about 2.5 hours with a little bit of break in the middle. So primarily it's pilot rating examination that we're targeting here, but it should be good for other things as well. The talk is derived from some stuff from Kenny Eaton, who's from the Dunstable Club, with further modifications from Nigel Page and Pat Dower, and then some more material and evolution of it by myself over the past few years, Mike Miller. So, as I've said, there are a few things that we're really targeting here. On a very basic kind of level, weather forecasting, you're really talking about, is the weather? Is there an absence of weather? Is it going to be a nice day? Once you become a pilot, you're then thinking, or you're under training, you're then thinking, is it going to be a flyable day? That's the most important thing to you probably. And then as you advance a little bit further, you're thinking, is it going to be a really good day? Is it going to be a day where I'm going to be able to take off and fly cross-country distance, maybe make a personal best or have a good long flight to somewhere that you've perhaps not been before? And then the final part, of course, is when you take all of those kind of things together, can we learn the things tonight that will enable us to pass our pilot exam if we're taking the pilot exam, or potentially to pass your CP exam or whatever, if you're at that earlier stage. So looking at the pilot exam stuff, the BHPA tells us about, in broad terms, what we're supposed to know. And this is basically a summary of what they state that you're supposed to be able to do basically to pass the pilot exam. So you need to basically be able to understand the relationship between wind direction and areas of high and low pressure. You need to be able to describe what fronts are and how cold fronts and warm fronts differ, and their action, what happens basically as they pass. What are the cloud formations? What sort of weather conditions do you see? What pressure changes and wind changes occur as a frontal system passes through? You should also be able to talk about different cloud types, the high, medium and low levels of cloud, and what sorts of clouds occur at that level. You should also understand how those different kinds of clouds are formed to some extent. And you also need to understand in detail the convective cycle and how convective clouds are formed, and specifically how you can work out at what height cloud base is, how strong thermic development is going to be, that kind of thing, and how those things relate to some fundamental atmospheric concepts like lapse rates, dew points, ground temperatures, that sort of thing. You should also be able to talk knowledgeably and understand some meteorological terms, stability and instability, what the wind is doing, whether it's veering or backing, the lapse rates that we'll talk about, what a tephogram is, what anabatic and katabatic flow are, that sort of thing. As I've said already, the conditions associated with high and low pressure systems and what happens when those are potentially moving through. You also need to understand some things that are meteorology related to terrain, relief and landscape features. So valley winds, which more tends to apply in alpine environments with big mountains. Anabatic and katabatic flow, which applies pretty much everywhere where you've got significant relief. Sea breezes and sea breeze fronts. Wave lift, and the various types of fog. So those are little relatively small scale phenomenon that you have to be able to understand and explain. You need to be able to talk about synoptic charts. You should be able to recognize the features on them, you should be able to describe the current weather and what is likely to happen at specific locations. And finally, you should be able to link cloud types to the associated types of precipitation you would expect to see along with them. So to start off with, it's always a good idea to try and go into some of the underlying physics in a very, very lightweight kind of way. And the first thing really that affects the way in which the weather works are the gas laws. And this is about the behaviour of the atmosphere, basically. Any gas follow these rules. The first one is that if you take a volume of gas, the pressure is proportional to the temperature. So if you increase the pressure, then you will also increase the temperature at the same time. Similarly, if you increase the temperature, you'll increase the pressure. And an easy way to think about that is if you are blowing up a tyre, things get hot. Or if you're releasing compressed air from a cylinder, the nozzle gets cold as the air is basically released and the pressure decreases. The other part of the gas law basically is that pressure is inversely proportional to volume. So if you take a fixed amount of gas and you basically increase the volume that it's taking up, then the pressure will go down. If you decrease the volume that gas is taking up, then the pressure will go up. And the easy way to think about that, if you're engineering type people, is a gas strut. Basically, if you've got a gas strut and you compress it, the more you compress it, the stronger it pushes back against you. If you expand a gas strut, the pressure that it provides against you is basically decreased. So that's the gas laws, basically. And that's quite important for understanding what happens to air as it moves up and down in the atmosphere and the pressure changes and that sort of thing. The next fundamental really is insulation, which sounds a bit like what you might have in your loft, but in fact, rather than insulation, it's insolation. It's about sunlight arriving and basically hitting the Earth's surface. And the important thing to remember here is that the air is pretty much transparent. When sunshine shines through the atmosphere isn't significantly affected at all by the sun's rays. There's no transfer of energy. The atmosphere is not warmed by the sun shining through it. However, the sun then hits the surface of the Earth, or whatever else, your face, a car, you name it, whatever it hits, and the body that it hits is warmed up once the sunlight hits it. And the air is then warmed by contact with the surface that has had the sun shining on it. So air in contact with the surface is heated by conduction, and it expands, and then close to the surface you then get convection occurring, which is basically the mixing of the air. So the very warm bit near the surface basically moves away from the surface, colder air replaces it, that is heated in turn, and that basically allows a layer of air that's thicker than a tiny little bit to be warmed by the sun. So air that's away from the surface is only ever warmed by conduction and mixing convection, basically. So that's insulation rather than insulation. If we apply these two kind of fundamentals, then we start to understand at a very large scale what's basically happening with the world's weather. The area on the Earth's surface that has the greatest level of insolation is the equator, because the sun is overhead, the atmosphere is, relatively speaking, thin, so the sun is shining straight through it, and it's shining straight down on the equator. So here you have the highest level of heating. That causes essentially convection at the surface. You get heating, convection, and you get a large-scale flow that's occurring, basically. And this flow close to the equator is called a Hadley cell, basically. So warm, moist air is basically heated by conduction, convection from the insulation. The air closest to the equator then tends to rise. It moves up into the atmosphere, it cools, it moves away, and then it cools down and slides and returns basically back in the same direction to repeat the cycle. So the Hadley cells basically are a broad pattern that's occurring pretty much all the time, and they tend to be about 30 degrees in latitude wide kind of thing. So that's what's happening at the equator due to the highest level of insolation being here. If you then look around the rest of the surface of the Earth, we have a pattern that kind of like repeats itself. So you have the Hadley cells near the equator, and then in the mid-latitudes you have feral cells basically. So we're sitting somewhere here kind of thing. And the feral cells basically, there's southerly airflow at the surface, and then heating, and it moves towards the horse latitudes, the doldrums, this area here. And then finally you have the polar cell basically, which is another cell that's occurring at the northernmost latitudes. So if you then take those three broad patterns of airflow and you apply a rather tricky little effect that we have to know a little bit about, called the Coriolis effect to them, then you will start to see basically why the prevailing winds are in different directions at different parts of the Earth. So what I'll probably do now is just try and explain a little bit about the Coriolis effect. If you had a pendulum and you set it up in a shack on the North Pole and you set it going and you went away and you came back 6 hours later, you would find that the pendulum was swinging at 90 degrees to the direction that it had originally been swinging when you set it off. And that is actually because when you release the pendulum, the Earth rotates underneath it. If you do the same experiment at the equator, nothing happens. At the equator, you let the pendulum go, you come back 6 hours later, and it's still going in exactly the same direction. So as you move from the poles to the equator, this kind of rotational effect, the Coriolis effect, gradually decreases. And the traditional story about it is the water going down the plug hole. That's not actually it's not a good example. There is no definitive direction in which water goes down the plug hole, because the Coriolis effect can only be observed at large scales. So large scales means over a long period of time or over a large distance. So if you have the pendulum swinging, it's small distances, but you're allowing it to act basically independently for 6 hours, so you can observe the Coriolis effect there. If an example of a long distance thing but relatively short time period is artillery firing of shells, they may fire for 25 kilometers or something like that, maybe further. And although they arrive relatively soon at their destination, because there's a very long distance involved, the rotation of the Earth underneath the artillery shell is actually noticeable and has to be adjusted for. So sinks and plug holes, no. Artillery shells, pendulums, and potentially airflows, yes. So what the Coriolis effect actually does to the air is it causes it basically to rotate to the right. When you have an airflow from an area of high pressure to an area of low pressure, the airflow is deflected to the right in the northern hemisphere. In the southern hemisphere, the opposite case occurs. You have a deflection to the left. And because of that, so we have the low pressure here at the boundary between the equatorial cell and the mid-latitude cell. This is low pressure, so we have air flowing other way around. No, this way. So yeah, we have high pressure here and low pressure here. The deflection is to the right in these latitudes where we are. So that basically means that the prevailing wind direction is kind of southwesterly. So the Coriolis effect basically means that we have this constant deflection that occurs to the air currents that are set up and are established for a long period of time. So yeah, here we go. So the subtropical high, which is in the doldrums, south of that you have southerly airflow, that is deflected to form easterlies. North of it, you have northerly airflow, which we're in, which is basically deflected to form westerlies or southwesterlies. And then at the poles, again, you have polar easterlies kind of thing. And the whole thing is repeated, but the other way around in the southern hemisphere. So that's, at a large scale, what the Coriolis effect does. On a slightly smaller scale, you basically have the situation where high pressure and low pressure areas in the atmosphere are preserved because of the Coriolis effect. So if you had a high pressure and a low pressure area adjacent to one another in a region where there's no Coriolis effect, the air would flow directly from the high pressure to the low pressure and pretty much equalise it out. And that's what tends to happen at the equator. You don't get large differences in pressure, basically, at the equator. Whereas in the mid-latitudes and the higher latitudes, because of the Coriolis effect, the air tries to flow from high to low, but it's deflected in the northern hemisphere to the right, and so you end up with basically circular motions. And the circular motion basically causes these high and low pressure systems to become established, to become more stable than they would otherwise be. So we don't end up with high and low pressure systems equalising out quickly, they tend to persevere. And as you can see from this diagram, the air actually flows in opposite directions around the two types of system. So around a low system, in the northern hemisphere, we end up with anti-clockwise flow. Around a high pressure system, we end up with a clockwise flow, basically. So a few little bits about the fact that we have these kind of like pressure systems that tend to persevere in our latitudes. The International Civil Aviation Authority basically sets out, because we have this variation in pressure, they set out what they deem to be a standard pressure, which is kind of like the average global pressure level, which is 1013.2 millibars, and you'll hear a little bit more about that when you learn about instrumentation, because that has quite a lot of, it's used in the standard ways in which we measure altitude. So standard pressure 1013.2 millibars, that's the average essentially of the kind of like global air pressure at sea level. If you move up 30 feet from sea level, or from anywhere from any particular altitude, if you move up 30 feet, then you will cause a decrease, or you will experience a decrease of 1 millibar in pressure. And this is how varioaltimeters measure the altitude that you're at and the rate at which you're moving up and down. They measure the pressure, and they can work out from the changes in pressure how much change in height you've been experiencing. The formal name for those two types of pressure systems, for a low pressure system, a cyclone is the name, but it's often called a depression. And for a high pressure system, an anticyclone is the traditional name from the meteorologists. So if we're looking at pressure systems on a map, then you'll be familiar to some extent with synoptic charts, and you can see the pressure systems represented on them by isobars, which are lines showing a particular constant pressure level. They're very much like contour lines on a traditional map. When we have wind that's a little bit away from the surface of the Earth, the wind tends to blow along the lines of the isobars in mid-latitudes. And that wind along the isobars is known as the geostrophic wind. And when you've got sort of, you know that the wind is blowing along the isobars, it's blowing from one place to another. This tends to then develop the idea of air masses, which is a body of air which is basically uniform. It's maybe stuck in one place, or it's moving from one place to another place. So an air mass is a kind of collection of air that has a common set of properties and is all going in the same direction or doing the same kind of thing. So, when we look at pressure systems and we have this kind of like idea of there's a high pressure that's established here and a low pressure that's somewhere else, then it's possible, based on the positions of those pressure systems, to make predictions about the wind direction. And as we already saw, the geostrophic wind blows along the isobars. But the question is, which way? Well, the way you answer that is by Buys-Ballot's law. And Buys-Ballot was a meteorologist back in the early days of meteorology, who noticed basically that if you're in the northern hemisphere and you stand with your back to the wind, then you will find that the low pressure will be on your left-hand side and the high pressure will be on your right-hand side. So if you then have a synoptic chart and you can see where the high and the low is, you can see the isobars between them, then you can imagine if you were standing with your left-hand side pointing towards the low and your right-hand side pointing, then the wind would be blowing straight from behind you. The easy way to remember this is that there are less left-handed people than there are right-handed people. Does that make sense? Maybe. Or yeah? The low pressure is on your left. There are less-handed people. Well, that's the way I remember it anyway. Perhaps if you're left-handed, that might feel a bit wrong, but it generally tends to work that way of memorising it. So that's Buys-Ballot's law, and it helps you to determine which way the wind is basically blowing when you've got a set of pressure systems that you can observe. So if we look at the two different types of pressure systems, so low pressure systems, generally that means that we have air that is ascending from the surface being moved upwards in the atmosphere. In the northern hemisphere, as we've said already, there is an anti-clockwise flow around low pressure systems. And there is actually, so we've already said that there's this concept of the geostrophic wind which blows along the isobars. Close to the surface of the Earth, friction between the wind and the surface of the Earth basically causes the air actually to blow closer to the direction of the high to the low, if you see what I mean, towards the centre of the low, basically. So close to the surface of the Earth, you have kind of like maybe 10, 15 degrees of direction in towards the centre. Further above 1,500 feet kind of thing, you then tend to have geostrophic wind that blows along the isobars. And this, from an observational point of view, that means that if you're in the area of a low pressure system and as you climb away from the surface, that means that the wind direction will tend to move to the right. If it's blowing in your face, it will gradually move in that direction as you move upwards. So that's low pressure systems, ascending air. So although it's low, the air is moving upwards, and we'll see what moving upwards air tends to mean later on. High pressure systems are very much the opposite. So in a high pressure system, we have air that's descending from higher in the atmosphere and coming down into the middle of the high pressure area. In the northern hemisphere, we have a clockwise flow. And again, friction with the surface tends to mean that as you get close to the surface, the wind moves a little bit further away from the high rather than blowing purely along the isobars. And again, it's the same rule. In the northern hemisphere, the wind moves to the right as you ascend when you're in the... so it doesn't really matter where you are. More often than not, the situation will be that as you climb away from the surface, the wind in the northern hemisphere will tend to move to the right. Particularly if you're kind of like in an area where the wind is basically being influenced by high and low pressure systems rather than other local phenomena. So that's a high pressure system, and how the wind around it is structured generally. So what do we know about the weather and such forth in the vicinity of these two types of systems? Well, low pressure, normally we have poor weather. We have frontal systems, which we'll look at a little bit later. We tend to get cloud and rain, and generally cloud and rain are associated with rising air, basically, and we'll see why that is a little bit later. High pressure systems in the summer, we'll often have, in the middle of high pressure systems, we'll have light winds. We don't tend to have very much cloud. We can tend to have stable flying conditions with inversions, which can mean that it's difficult to climb high, kind of thing. In the winter, some high pressure systems tend to result in fog and low cloud, and those kind of like grey days where you can't see, the visibility is very poor, it's Tupperware sky, that kind of thing, not much wind, grey and muggy winter days. Or you can also have high pressure systems in winter where it's very clear, extremely clear. And that just depends upon the air mass that's associated with a particular high pressure system, where it's come from, whether it's cold and dry air or whether it's moist air, basically. So, a synoptic chart. We can see some pressure systems on here. This is one from January a few years ago. You can see that there's a large high pressure system in kind of like mainland Eastern Europe. We've got a pretty vigorous low system north of Scandinavia. And you can probably, from Bayes-Ballott's law, you should be able to work out what the direction of the wind will be around about, you know, in the Baltic area. As you can see, on the left-hand side is the low, on the right-hand side is the high, so the wind is going to be westerly there, blowing along these lines, more or less, along these isobars. We've got some other low-pressure systems over here, smaller ones kind of thing in the Atlantic. We'll have a look at some of the other symbols on the charts which are associated with frontal systems and troughs, etc. Shortly, but you can see pretty much all of the features that we've been talking about there in terms of high and low pressure systems on a synoptic. So yes, cyclones and anticyclones, isobars. The isobars, as we said, link areas of equal pressure, points of equal pressure. The pressures are shown in millibars, and where you have isobars that are very close together, that tends to mean strong winds, basically. When you have isobars that are widely spread, that means light winds more often than not. And the wind directions, you can determine them by using Bayes-Ballott's law and looking whereabouts the high and low pressure centres are, and assuming that the wind blows pretty much along the lines of the isobars. Now, for the pilot exam, you need to know some old meteorological terminology in terms of wind direction change. And this all comes probably from from sailing school teaching of weather, really. You'll be very unlikely to hear someone who's a pilot say that the wind was veering or the wind was backing, whereas a sailor might potentially say that. Veering basically is the normal wind direction change. It's basically when the wind goes round to the in the clockwise direction, so it blows more from your right. We've already described the fact that as you climb away from the surface, more often than not, the wind will veer. In the northern hemisphere, the Coriolis effect causes the wind to veer, basically. Backing is the opposite change in direction, so the wind changes in an anti-clockwise direction or blows more from the left-hand side, and that's more unusual. I'm not sure that your soundtrack is going to be much use, I'm afraid. Potentially, once I start, I may be in difficulty. So the next thing to think about is really clouds. Now we've looked at pressure systems a little bit. How do clouds form? When you have higher temperature air, you can basically have more water vapour contained within the air. Basically, is the fundamental underlying rule that that basically should help you to understand how clouds form. So, at high temperatures, think of steam. Then you can have a lot of water vapour actually in the air. At lower temperatures, the air can actually hold less water vapour. And when you get air with a lot of water in it that's at a high temperature, with a lot of water vapour in it that's a high temperature that is cooled, then you reach the point there, what's known as the saturation point, and what's also known as the dew point temperature. And any further cooling basically causes condensation, so the water vapour in the air actually comes out as little tiny drops of water. And that happens at the dew point, basically, once 100% saturation is reached during the cooling process. So, to express that all in a kind of like single, slightly more scientific sentence, for a particular pressure and temperature, a certain amount of water vapour may be present in the air. And when you cool an air mass below that point, whilst not doing anything else, or you decrease the pressure, then you basically cause water vapour to condense out. So condensation basically is what forms clouds. So we have a bit of a look at some different cloud types. Here's a nice sunny day with some convection clouds, and in the distance there's some sort of layer cloud thing going on, which is quite interesting. We'll have a look at those different types of clouds shortly. Again, here we've got, this is probably in Spain, I think. We've got more convection clouds, deeper convection, a bit more margy, as some people tend to say, or caulifloral. And you can see that over here there's something else going on, kind of thing, which is probably that one of these clouds may have got a bit extraordinarily large. Oh yes, here we go. Another photo from later on the same day, I believe, where you can see that there are still some small convection clouds knocking around, but in the background there's evidence of very large scale convection and probably a thunderstorm forming, kind of thing, a cumulonimbus cloud. Here's a little bit of closer to home sort of picture, taken in the peaks, and we can see a mix of cloud types here. There's some low-level convection clouds, some convection, and well, so slightly stratusy, slightly convection-y stuff going on, and then it appears that there's some higher-level sheet stratus cloud that's knocking around. So we've got a different mix of cloud types here. So let's have a little bit of a look at how those different sorts of clouds form in a bit more detail. The convection sort of thing that we've touched on so far, we have insolation. The action of the sun heats the ground. This in turn heats the air close to the ground, which the gas laws indicated as it becomes warmer, it will become less dense. Because the air close to the ground is less dense, it may then rise when it's replaced by colder air from elsewhere. And as it does so, as it rises, the pressure decreases as the air rises, which means that the air parcel decreases in temperature. Again, the gas laws. So you end up with rising air through convection, which cools. Eventually, that parcel of air might cool far enough to actually reach the dew point, depending upon how much water vapour there is within it. And once it reaches the dew point, if it carries on rising any further, it will be cooled sufficiently to cause water vapour to condense out to form clouds. Normally, when you have convection, the type of clouds that you're going to see are cumulus clouds, little fluffy clouds kind of thing, or possibly larger fluffy clouds, as we saw in some of those pictures. So that's cloud formation via convection. You can also have what's known as orographic uplift, which is basically the terrain, the relief in a particular area, causing air to be forced upwards. So if you have a wind flow and a mountain chain that blocks that wind flow, the air will tend to be forced up over the mountain chain, and as it is forced upwards, it will cool again because the pressure decreases, therefore the temperature decreases. And again, if it cools below its dew point, then you end up with water vapor condensing to form droplets of water, which forms orographic cloud. And this tends to occur on the windward side of the obstruction that the air is being forced over. So here we've got some convection clouds. They're small and fluffy and pretty much fit the first description. And this is a fairly obvious kind of like case of orographic cloud. There was a lovely video posted on the internet a couple of weeks ago by Kelly Farina, which actually showed large-scale orographic cloud on the opposite side of the Alpine range, basically, which had been forced upwards, and you had huge-scale orographic cloud formation. And then it was someone driving along a road which was just on the lee side of the Alps, and you could see the cloud basically the air coming back down again, and as it warmed, the cloud actually dissolved, kind of thing. So you could see that the same kind of thing would be happening behind this hill as the air comes back down again. The dew point is then reached in the opposite direction. The air gets warmer than the dew point, and potentially the cloud then dissolves behind the hill, kind of thing. So that's orographic cloud. You can also have a kind of like mixture of the two, and this often happens in sort of like alpine environments where you have upslope flow of air, basically thermal flow up the slope, which we call anabatic, and we'll talk about that in a little bit more detail shortly. But as the air flows up the face of the hill, you will tend to get cloud formed once you're above the dew point. So that's due to thermal flow rather than due to wind flow, basically up terrain. So then there are some other kind of ways in which clouds are formed which produce markedly different sorts of cloud formation. And one of those is widespread lifting. So there are certain atmospheric conditions under which large volumes of air basically are all lifted together. And the typical one of those is when you have two air masses that meet in a frontal system normally, then you basically end up with a wedge of colder, denser air moving under the warmer air, which is lighter. And as that happens, the warmer air is lifted, forced to rise, and as it rises, it cools, and then you end up with large areas of sheet cloud, basically. You can also get cloud that is formed at a turbulent layer where you have mixing that's occurring. And despite researching this a little bit, I cannot find a sensible explanation for how it works. But basically, if you have two air masses that are moving over one another, and you have a layer in between them that's essentially mixing, then you can get cloud formation in that layer as well. So here we've got a couple of different things going on. There's obviously widespread lifting because there's kind of like sheet cloud that's developed, but also because we've got a sort of like wavy mackerel sky pattern, it looks like there's some kind of wavy, sheery, something else is going on as well, basically to prevent it just from being a flat Tupperware sky. There's a combination of factors going on in this particular shot. Here again, we've got some convection cloud down here, but then we have some very high level. This is cirrus cloud, basically forming a nice mackerel sky, and that's at very high level caused by lifting. So stop doing that. Here's another pattern of clouds caused by a shear layer, essentially. These clouds that are a little bit like white horses or seahorses are actually called Kelvin-Helmholtz clouds, and they're caused by a wave pattern being set up basically between two separate layers of the atmosphere, and in the turbulent wave layer that is formed, you actually end up with these repeating cloud formations, which, if you look into the sky on a wavy day, you may sometimes see interesting repeating patterns, which is caused by this particular effect. And here is your classic Tupperware sky. Probably this is in the vicinity of a warm front. You've got very little in the way of kind of like features or distinction in the cloud layer. It's just basically a flat uniform cloud layer caused by extensive widespread uplift of moist air. So still further cloud formation types. When we have wave activity, which we'll talk about a little bit shortly, you can get lenticular cloud formation, and you have a wave formation in the atmosphere. At the top of the wave, basically where the wave reaches its highest point, you end up with a cloud that develops, and then as the wave flows through, it then decays on the other side, kind of thing, and the cloud remains stationary and doesn't move with the wind because it's basically staying on top of the wave, which the wind is blowing through. You can end up with quite spectacular lenticular formations where they're basically stacked one on top of the other as well. If you see lenticulars, generally that tends to mean strong wind and potentially strong wave-related turbulence, so it's a good sign to be cautious in terms of planning your flying activities. So we've got a few pictures of some wave clouds here. This again looks like it's somewhere probably Spanish, most likely. You can see there are some mountains here, and there's a very large high-level wave cloud, fuzzy edges, and that cloud is probably going to be stationary there for several, half an hour plus kind of thing, not moving with the wind, whereas these little convection clouds will be moving around kind of thing. Here are some more rather closer to home sorts of wave clouds. I think Ash posted a nice video of some Lee wave in the Peak District the other evening that he'd taken from a car park in Sheffield. But this is the same kind of thing. You can see they're kind of like lens-shaped clouds that are thinner at the edges, thicker in the middle, and they're kind of like static. You can see, if not stacking, you can certainly see sequences of clouds, basically as you've got the top of one wave and then the top of the next wave and the top of the next wave moving downwind. You can see there's probably some high cloud above as well of some description. And then we often get kind of hybrid situations. You might think that this looks like a Peak District day with just convection cloud. But in fact, it's probably a combination of convection cloud and wave influence. So this massive cloud here, most likely, is probably not going to move towards the hill you're standing on very much. It will probably shift and change shape, but it will probably remain there quite likely. It won't necessarily come towards you because there's a wave system potentially set up here. You can see a blue slot beyond, and then there's another kind of like bluer slot here, and the wave that's blowing through encourages convective development underneath it, and then it suppresses convective development where it's coming down again, kind of thing. So you'll often see these kind of like, there's an area of cloud here, it's sticking here, it looks like convective cloud, but it's not really moving towards us. And similarly, there's a blue area in front of and behind it, kind of thing. That's a kind of like mixed wave and convection pattern, and you'll often see that. And what will tend to happen as the day goes on, you get into late afternoon, and these shapes will start to look less convective and more wavy. You're driving home from maybe you've been on a cross country or something like that, it's been a nice flying day, you're driving home or you're on retrieve or whatever, and you'll tend to, as you look into the sky, you'll see that the convective patterns in the sky are actually decaying, and you're now seeing the underlying wave that has been there all day, that's been influencing the convection. So that's quite a common thing to kind of like experience. It's a good thing to recognise as well, because if you can spot the days where there's some wave mixed in with the convection, then you can make better predictions about, what to do, how to fly, what sort of thing to expect, kind of thing. Now this is wave again, but this is wave with stratus. Wave with kind of like mid or low level stratus, which is often the case. You often see it in the vicinity of warm front, in the vicinity of a warm front, and basically you've got a relatively low level set of stratus clouds, and basically there is a wave pattern, and you can see the wave pattern reflected in the underside of the stratus clouds. I think the guy from the Cloud Appreciation Society or whatever who wrote that book has succeeded in getting this particular cloud form named as something like Aspiratus undulatus or something like that he's come up with. I think it probably had a name already, but anyway, the Met Office someone's accepted it, so but yeah, that's wavy stratus cloud, basically, low-level wavy stratus cloud, which you'll quite often see if you look for it. So here's a bit of a summary of some of the different cloud types. We have the high-level clouds, which tend to be called cirrus or cirro, which relates to ice, basically, because they're so high that they are composed of ice crystals. You've got cirrocumulus, which are very small, kind of like little puffy clouds, very, very high up in the sky. You have your traditional cirrus, kind of like mackerel or sheety, kind of like high-level clouds that look like chalk marks or whatever on a blue sky. And obviously, cumulonimbus clouds can go very high as well. So they're kind of like they're a law unto themselves. They don't really fall into the what height are they category, because they pretty much cover all the heights. So you have the cirrus clouds, you then have altus clouds, which are 6,000 to 20,000 feet. So again, you have altocumulus, which are again relatively small convection clouds, and you have altostratus. So the alto clouds, they're mid-level, 6,000 to 20,000 feet. Cirrus clouds are 18,000 feet and above. And then you've got the lower level clouds, stratocumulus, which are basically convection clouds with some kind of like flat layer cloud properties. Stratus clouds, which basically pure flat uniform layer clouds. Cumulus, your traditional fair weather, nice soaring day kind of clouds. And then when you have very, very deep atmospheric instability, you have cumulonimbus, which literally means, dark cumulus or raining cumulus, basically. Black cumulus. So you should know about these different cloud types and their heights. You should know a little bit about how they should be formed and where you would expect to see them, kind of thing, in terms of on the weather chart and in relation to frontal systems. A little bit more detail about these. There are some abbreviations that are used on old style weather charts and weather reporting charts, and it's good to know those as well. So high clouds are generally 15,000 feet to 40,000 feet, as we've discussed. Mid, which are often called alto, 6,000 feet to 20 something potentially, and then the low ones are kind of like below 8,000 feet. Cirrus, a CI, cirrocumulus, a CC, cirrostratus, a CS, altocumulus, AC in the mid clouds, altostratus, AS, and then the lower clouds, stratocumulus, SC, stratus, ST, nimbostratus for grey and raining, NS, cumulus, CU, and cumulonimbus, CB. So stratus means layered, cumulus means heaped, cirrus apparently means hair-like, and nimbus means raining or dark. Okay, so that's clouds. Let's have a look at the next thing, which is fronts, really. So we're back to a synoptic chart here, and we can see on the synoptic chart we've got an anticyclone. There's not much in the way of fronts marked in the area of the anticyclone, and that's quite normal. Frontal systems don't tend to break into areas of high pressure, but in the vicinity of areas of low pressure, like over here, and particularly in this particular area here, we have frontal lines drawn on the synoptic, and there are three different categories of conventional front that are indicated here. There's at B we have a warm front, which you can basically see by a line with semicircles on the front of it. And at A we have a cold front, which is basically indicated by the triangles. Cold and frost-like is the way that, spiky, like icicles is the way that I tend to remember it. And then you have a third kind of type, which is basically an occluded front, which is actually a combination of a cold front and a warm front, and we'll see about that shortly, which is indicated by both symbols together. The rounded warm front symbol and the triangular cold front symbol. So frontal systems tend to develop and more often exist in the area of depressions. You also have a kind of like pseudo front, which isn't necessarily associated with a depression, called a trough, and that's just indicated with a bold line, basically. So, if we have a look at a more classic example, this is your classic textbook depression that you will, if you're going to be asked about something in your pilot exam, this is the sort of shape of depression that they'll probably ask you about. So you have the warm front, again, as we've said, and you can see this is in colour, so now you can see that the little semicircles are red. That's handy, isn't it? Indicating the warm front. And then behind the warm front you have what's known as the warm sector, which is basically, this is the warm air mass that has arrived, basically, when the warm front pushed through. And then behind that you then have a cold front, which then takes you into the cold sector, which is this new cold air pushing down and basically replacing the warm sector air. And again, you can see that the two fronts are basically meeting up here and then are forming an occluded front, which has both the warm and the cold symbols on it. So we'll see why that develops very shortly. It's due to the difference in characteristics between the two types of fronts, basically. That is your classic UK here's meteorology frontal example. So, talking about the warm front in a bit more detail, what's actually happening at a warm front is that an area of warm air, a warm air mass, is catching up with an area of cold air and basically rides up over the top of it. So the warm air is lower density, again due to the gas laws, and when it basically blows in to the area of where the cold air is, the warm air basically tends to ride up over the top of the cold air. And this kind of wedge effect is, it's a very shallow slope, 1 to 50 to 1 to 400. And the warm air is basically rising up over the colder wedge over hundreds of miles, basically. It's a relatively slow process. It's not a very vigorous kind of like change of the air mass. And it results in basically, as the warm air is gradually raised, as it rises up over the cold air, you get a gradually thickening set of layer clouds, and eventually, as you approach the frontal zone, you start to get rainfall until it eventually becomes like constant, steady rain, basically. So it starts off with a little bit of high cloud, gradually develops into extensive layer cloud. The layer cloud thickens, lowers. You end up with a little bit of drizzle to begin with. That becomes more constant, and then eventually it's like continued, persistent rain. And as I said, it's not a vigorous system. It's a slow-moving, gradual development in a warm front. So here's a diagram of that whole process. As you can see, the vertical scale is somewhat exaggerated. If that's 600 miles, then that's 20,000 feet. But you get the general idea. So as an observer here, you basically see that what happens to begin with is you start to see very small amounts of high cloud coming in. The high cloud gradually thickens. The cloud basically gets thicker and lower as the front moves past the observer. And then at some point it starts to mizzle, drizzle, rain quite heavily, rain quite a lot, raining significantly. And the cloud is lowering all the time, kind of thing. And then eventually you end up with the situation that the warm air is basically, the front has passed at this point, and you're now in the warm sector. And quite probably in the warm sector there'll be a clearance, the cloud will dissipate to some extent, and the rain will stop. Because the warm air in this sector is no longer being lifted, so it's quite happy not to rain on you, and you don't expect to see extensive cloud formation, kind of thing. So, as this diagram indicates, the frontal zone can be 600 miles wide. It's quite a big, long, great big, gradual progression towards horrible weather. You start off with cirrus and cirrostratus, and it shuts down the solar activity. It's what people normally complain about when they're on cross-country in front of a warm front. Oh, high cloud came in, shut down the thermal activity, I landed, kind of thing. So that's pretty normal, and you'll often hear about high cloud ruining someone's cross-country flight. And then the cloud base, as we said, it gradually lowers. You start off with altostratus, and then it goes into nimbostratus, i.e. it's raining, drizzle, and then heavier rain, kind of thing. And the rain's normally 5 to 10 hours before the front actually passes over the point of observation. The winds can strengthen and they can back as you basically approach the front, and then at the front the rain eases off. The wind normally veers around 50 degrees. It goes round into the kind of into the south, and the temperature and humidity rises up, basically, and then we're in the warm sector. So that's the process of a warm front coming through. As we saw on the chart, behind the warm front, more often than not, there is a cold front. And a cold front is basically where you have cold air. So a warm front was warm air riding up over stationary cold air. A cold front is the opposite. It's cold air basically coming in and undercutting warm air. A cold front is basically a steeper slope, and there's the whole lifting process that's involved in a cold front is a lot more vigorous. You get strong updrafts that are produced basically as a result of this cold air coming in close to the ground. You can have rapid development of heavy showers, and because the whole thing is much more vigorous, it's a cold front is a relatively fast-moving beast in comparison to a warm front, and we'll see that explains something else that we saw in the diagram shortly. So here's the diagram of a cold front. Again, there's a lot of exaggeration of the of the scale, but basically you end up with a relatively short frontal zone. Maybe 100 miles in front of the front is kind of like starts to have the cold front character, and then some period behind it as well, another 200-300 miles behind potentially. It's relatively fast moving. When you get to the front, basically the temperature drops significantly. The wind will tend to veer, often into a northwesterly direction, and you end up with cumulus and cumulonimbus potentially developing, often with heavy rain showers. You can get thunderstorms, lightning, that kind of thing in the summer quite often. And behind the cold front, there's often a complete clearance. So as the cold front goes through, the sky will often go right from cloud and rain to clear, and then you start to get showers developing, kind of thing, with cumulus and cumulonimbus formation again occurring behind the front. So the arrival of the cold front, relatively speaking, is a much quicker process. You don't have this long build-up. You just have a bit of high cloud that comes on, cirrocumulus, altocumulus, and then suddenly a big development of cumulus occurs. Then it starts to rain, and then you get this clearance behind it, basically into showery, unstable weather. Now, we've already described the fact that the cold front, a warm front, is a bit of a sluggish, kind of like leisurely beast that like gradually builds up and moves slowly through the point that the observer is at, and that a cold front moves faster. So that actually means that the two tend to catch each other up. The cold front will tend to, if there's a warm front in front of it, it will tend to catch it up, basically. And when it does catch it up, it forms an occluded front. So an occluded front basically has some of the it's got a hybrid of the characteristics, basically, of a warm front and a cold front. You end up with the build-up into the frontal area is a bit like a warm front, and then as the front passes, the tail end of it is more like a cold front kind of thing. And it's basically because this pattern is what's happening. The cold air and the, relatively speaking, cool air, basically. And this is fast-moving cold air, and this is slow-moving cooler air. They basically are coming together, and the warm air is gradually being squeezed. And when the occlusion actually develops, the warm air has been squeezed, and it's like totally nipped off the surface, kind of thing. So at the point that the warm air mass has basically been lifted completely away from the surface by the two colder air masses, then that's when the occlusion forms. And as we've said, that is something that tends to happen in most frontal systems. In a classic frontal system where you have the triangular shape of the fronts, the cold air base, the cold front basically will tend to catch the warm front up and develop an occlusion coming down from the northern part of the frontal zone, kind of thing. So, if we have a look at a bit of a summary of the whole frontal topic that we've looked at, a front is a boundary between two different air masses, and it's more commonly found in depressions than anywhere else. A cold front is marked by the spiky blue symbol on a line. The leading edge of an advancing cold air mass is what it is, and the line is basically where that air mass is on the ground, at ground level. The direction in which the triangles point is the direction in which the front is moving. And a warm front is kind of like the opposite. It's the leading edge of an advancing warm air mass. on a synoptic chart again, it's this red line with semicircles, and the red line marks the point at which that warm air mass contacts the ground. The direction is facing in the direction that the semicircles point. An occlusion is a combination of the two symbols on a line, basically. And the line basically marks the borderline. The line marks the borderline between the two cold air masses, because the warm air mass has been occluded away from the surface. And then we have these strange beasts that you saw on the synoptic earlier, which are troughs, which are marked by a line without necessarily any of the front type symbols. And these are basically localized low pressure areas where there's significant precipitation, but there aren't separate air masses that are coming together that are causing that. So you can have an area that has some frontal characteristics, but you don't have distinct air masses that are generating it. Often you'll see troughs where you have very cold air that's coming at high speed into an area, and you will see within that cold air mass there are trough lines that indicate where there are lines of showers. Basically, it's pretty common in very cold, very unstable air to see trough lines. So they're lines of more organised precipitation, basically, within a single air mass. We could probably, pause for a quarter of an hour at this point, and then we'll go into some more small-scale